You know that feeling when you're staring at just like a huge amount of information, trying to find that one specific thing you need?
Yeah, absolutely.
Well, for developers, that's pretty much a daily reality, especially when hunting for a particular piece of code.
Right. We call it code search.
And it sounds simple, maybe, but it's actually a really big deal.
Oh, definitely. It's far more than just convenience. Efficient code search is absolutely vital.
For what exactly?
Well, for reusing existing code, for finding solid examples when you're building something new, and maybe most importantly, for helping new developers get up to speed quickly, in a massive code base.
Makes sense. But the standard approach, for years, it relied on these encoder-based models, right? Like CodeBird or
Yeah,
Unixcoder.
exactly. And they were foundational, no doubt, but they definitely came with some significant limitations.
Right. Like they don't generalize all that well to new types of code or maybe different kinds of queries people ask.
That's one big issue. And the other.
The other huge roadblock, especially for real-world code, is that they really struggle with long code snippets. Their input lengths are just so restricted,
Yeah, we're talking something like 512 tokens for CodeBird.
which, let's be honest, that's often just not enough for complex functions or files developers actually work with.
Exactly. That input length thing was a real bottleneck.
Mm-hmm.
But it's also about how they were designed. They're good at representing code, but maybe not truly understanding it in a deep conversational way.
Okay, so that's where the new guys come in. Large language models, LLMs.
Precisely. Specifically the decoder-only kind, like ChatGPT or DeepSeek Coder.
And their potential seems enormous.
It really is. Because they have vast pre-training, they're much larger, and crucially, they can handle much longer inputs.
So you'd think they'd be the perfect solution for code search.
You would think. But surprisingly, their effectiveness specifically for code search hasn't really been explored systematically. Well, until now.
And that's our mission today. We're going to take a deep dive into how these cutting-edge decoder-only LLMs actually perform on code search tasks.
Right. We're looking at a recent study that did just that. Systematically evaluated 9 state-of-the-art models.
Across different fine-tuning methods, different data sets like CodeSearchNet and Cosquay Plus, and they even looked at different model sizes.
And spoiler alert, there are some really surprising findings coming up.
Yeah, findings that could fundamentally change how we think about finding code.
Okay, so maybe let's take a step back first. Code search itself, it's really evolved, hasn't it?
Oh yeah, way back it was just simple keyword matching.
Which, as you can imagine, was super limited. The way we talk is just so different from how code's written.
Totally different languages almost.
Pretty much. But then deep learning came along.
And that massively improved the semantic understanding, right? Moving beyond just keywords.
Exactly. And that's when those encoder-only models we mentioned, CodeBird, Unixcoder, really became the standard.
How did they work, basically?
The idea was clever. They convert both the natural language query, like how do I sort a list, and the code itself into vector embeddings.
Okay, like numerical representations, fingerprints.
Yeah, basically numerical fingerprints. Then they just find similarities between those vectors. Code that's numerically close to the query is assumed to be relevant.
But even with that advance, they still had issues. You mentioned two big drawbacks.
Right. First, that poor generalization again. These models are often, relatively small. Unixcoder, for example, has fewer than 100 million parameters.
Which sounds like a lot, but in LLM terms?
It's not huge these days, no. And they're often fine-tuned on fairly narrow data sets. So when they see new kinds of queries or code, they struggle.
Okay, that's generalization. And the second one?
The input length limit, again, it's maybe even more critical. They just can't handle long code snippets effectively.
So the code gets cut off? Truncated.
Exactly. Important parts of the code might just get chopped off, and obviously you lose semantic meaning.
Which tanks your search results. Like trying to understand a recipe when half the steps are missing.
Precisely.
Yeah.
So that really pushed researchers to look for better solutions.
Okay, so we've got the limitations of the old guard. Now the big question, how do these powerful new decoder-only LLMs stack up right out of the box?
You mean in a zero-shot setting?
Yeah, exactly. Just throwing them at the task with no specific code search training, testing their raw capabilities.
Okay, so the researchers did exactly that. They evaluated them on 2 key data sets. First, CodeSearchNet or CSN.
That's a pretty standard benchmark, right? Multi-language?
Yep, widely used. And second, CodeSQA plus MOOF.
Right.
That one's newer, Python-specific, and actually more challenging.
Why more challenging?
Because it includes multiple correct code answers for each query. Makes it a tougher test of relevance.
Got it. And they used metrics like MRR and MAP.
Right, mean reciprocal rank and mean average precision. They basically measure how quickly you find good results and how many good results you find near the top.
Okay, so
Mhm.
the results. Drum roll, please.
Well, this is where things get really interesting and honestly pretty surprising.
How so?
In the zero-shot setting, the encoder-only model, Unix coder, actually significantly outperformed all the decoder-only LLMs.
Wow, really? By how much?
A lot. Unix coder hit an average MRR of 0.660 on CSN, the best decoder-only model in zero-shot. That was Llama 3, and it only managed 0.239.
Whoa,
Uh,
that's a massive gap. Why?
It makes sense when you look at how they're built. Unix coder was specifically pre-trained using multimodal contrastive learning, meaning it was explicitly taught to understand the relationship between code and natural language descriptions, to learn good representations for both and how they connect.
Okay, designed for the job.
Right. Decoder-only models, on the other hand, are mostly trained on next token prediction, predicting the next word in a sentence.
Which is great for generation, but maybe not for this kind of search task.
Exactly. It's not optimized for creating these meaningful, comparable embeddings for code and queries in the same direct way. Plus, their basic causal attention mechanism.
That's the thing where they can only look forward, not backward, when processing text.
Yeah. Makes it harder for them to get a complete understanding of a whole query or code snippet all at once. Great for writing, less great for deep analysis of existing stuff.
Okay, that explains the gap. But here's another curveball from the study, right? About code-specific LLMs.
Ah, yes. Another counterintuitive finding. You'd automatically assume that LLMs specifically trained on code, the code LLMs like CodeGemma or Mistral's code models, would do better.
But they didn't always.
Not always, no. In these zero-shot tests, they sometimes perform slightly worse than their general-purpose counterparts after that extra code training.
Huh. Why would more code training hurt?
It suggests a tricky trade-off. Maybe they got better at understanding code syntax, but lost some edge in processing the natural language queries effectively.
So it's a balancing act. You need both.
Definitely. Deep code understanding and strong language comprehension.
Interesting. But you said Llama 3 was the best of the decoder bunch in zero shot?
It was, yeah. It stood out.
And the thinking is that's down to its training data.
Exactly. Its pre-training corpus was just enormous, over 15 trillion tokens.
Oh, wow.
That's like 7 times bigger than Llama 2's dataset. And crucially, it included 4 times more code data.
So sheer scale and data diversity gave it an edge.
It seems so. It demonstrates the power of just seeing massive amounts of diverse data for generalization, even without specific task training. It just had a better foundation.
So the big takeaway from zero shot seems to be that pre-training really matters, what the model was originally designed to do.
Absolutely.
Yeah.
It gives us a baseline, but highlights that the objective during pre-training and the data scale are hugely impactful for how well a model starts on a new task. It's not just being smart, but being smart in the right way for the job.
Okay, that sets the stage perfectly because the zero-shot results were, frankly, a bit disappointing for the big LLMs.
There were. It looked like the old guard was still winning.
But then, the researchers introduced fine-tuning.
And this is where the narrative completely flips.
What method did they use for fine-tuning?
They primarily use supervised contrastive learning, or SUPCON.
Okay, SUPCON. What does that do?
It basically teaches the model to pull embeddings for relevant query code pairs closer together in that numerical space we talked about.
And push irrelevant pairs further apart.
Exactly, making the distinction much clearer for the model.
But wait, didn't you say decoder models struggle with understanding full context because of that causal attention thing? How did they handle that for fine-tuning?
Good point. The researchers addressed that. They adapted a bidirectional attention mechanism, allowing the model to look both ways, essentially, and also used masked next token prediction training before the SUPCON fine-tuning.
So they kind of retrained them to understand context better first.
Yep. Gave them the tools they needed before teaching them the specific code search task.
And the results after this fine-tuning.
Absolutely dramatic improvements. Night and day.
Like how dramatic?
All the decoder-only LLMs showed massive gains. The average MRR on CSN shot up by between 450% and, get this, over 700% compared to the zero-shot scores.
Wow, that's an insane leap.
It really is. But here's the kicker.
Go on.
With fine-tuning, the tables completely turned. After fine-tuning, the decoder-only models significantly outperformed the encoder-only models.
So Uniscoder lost its lead?
It did. In fact, Uniscoder's performance actually declined on the COSCUDA Plus dataset after it was fine-tuned on CSN.
Why would fine-tuning make it worse?
Likely overfitting. It probably got too specialized on the specific types of queries and code in the CSN dataset, and then couldn't generalize well to the different style of COSCUA plus SYN.
Interesting. So who was the winner among the fine-tuned models?
CodeGemma really shone through. It became the top performer after fine-tuning.
How much better was it?
Well, on CSN, it showed about a 5.6% improvement in average MRR compared to the fine-tuned Unix coder, which is solid.
Okay, but the real test is generalizing, right? Like on
Yeah.
CodeCo clustering.
Exactly. And on COSCUA plus, remember, neither model was fine-tuned on this dataset. CodeGemma showed a huge 49.6% increase in MAP and a 41.3% improvement in MRR compared to the original zero-shot Unix coder.
That is seriously impressive generalization.
It absolutely is. And what this tells us, really, is that the larger size and richer pre-training of these decoder-only models allows them to soak up more knowledge during fine-tuning and generalize that knowledge much better to new, unseen datasets like COSCUA plus X.
So the potential was there all along, it just needed the right kind of training to unlock it.
Precisely. It's not just about the raw power, but how you refine and direct that power for a specific task.
Okay, so fine-tuning is the key. And let's dig into why it works so well. The study looked at a few factors, right? Starting with the training method itself.
Yep. They compared that supervised contrastive learning, subcon, with an alternative, unsupervised contrastive learning called SIM-CSE.
And which one worked better?
Subcon was significantly more effective. It dramatically improved the model's ability to tell the difference between relevant and irrelevant code snippets.
Why was it better than the unsupervised method?
Well, SIM-CSE offered some improvement over zero-shot, but it wasn't nearly as impactful because it doesn't explicitly use labels telling the model which pairs are positive, relevant, and negative, irrelevant. Subcon uses those labels.
So having that direct supervision makes a big difference in learning those distinctions.
A huge difference. It's like being explicitly told what to look for versus trying to figure out yourself with only vague clues.
Okay, so the method matters. What about the data used for fine-tuning, specialized code datasets versus more general ones?
Right. They compared fine-tuning on code search datasets like CSN versus using general information retrieval datasets like one called E5.
And I guess the specialized datasets worked better.
They did, yes. More efficient, better performance lift using the code-specific data. No big surprise there.
But
Oh.
I sense a but coming.
But here's another fascinating detail. Even the generic information retrieval datasets could still effectively enhance the performance of the decoder-only models.
Even without code-specific examples.
Yeah. Particularly for models like Llama 3. It suggests their strong underlying generalization abilities, thanks to that massive pre-training, allow them to benefit even from broader types of retrieval training data.
That's actually huge from a practical standpoint, right? Getting massive, high-quality code search datasets is hard.
Exactly. It's expensive and time-consuming. This finding suggests there might be more accessible paths to building powerful code search models, maybe leveraging existing general retrieval datasets.
Interesting. Okay, what about model size? Does bigger always mean better here?
Generally, yes. The study confirmed that larger models tend to perform better. For instance, Llama 213b outperformed its smaller 1.3b and 7b siblings.
But isn't always the answer, just scale up.
Here's the twist. No, it's not a silver bullet.
Mm-hmm.
Even the big Llama 213b model didn't actually match the performance of the fine-tuned CodeGemma.
Ah, so size isn't everything.
It seems not. It highlights that the model architecture itself and maybe the specifics of its initial pre-training focus are also incredibly important factors, not just raw parameter count.
Like building a race car, you need more than just a giant engine. The design, the tuning.
Exactly. The whole package matters.
So, pulling it together, what are the main strengths and weaknesses of these fine-tuned decoder models for code search?
Their big strength is definitely handling longer queries and longer code snippets. That's where encoder models really fall down. The larger capacity of the decoder models allows for a much better, more holistic understanding of complex code and detailed requests.
Makes sense. But where do they struggle? Is there a weak spot?
Yes, the study identified a significant one. Performance drops noticeably for very short queries, specifically queries with fewer than about 10 tokens.
Fewer than 10 tokens. Why would they struggle with short, simple queries?
It seems to be linked to a couple of things. One is the classic cursive dimensionality.
Okay, break that down.
Basically, with only a few words, the resulting embedding vector is very sparse. It doesn't have much information in it. In the incredibly high dimensional space these models work in, trying to find a good match based on such a sparse vector is really, really hard.
Like trying to find a specific person in a giant city using only their hair color.
Kind of, yeah. Not enough distinguishing information. And the other issue is just lack of context.
The short query just doesn't give the model enough to go on.
Exactly. The semantics might be unclear. This can lead the model to latch onto simple keyword matches in longer code snippets, even if they aren't actually relevant to the user's intent.
Okay, that's a definite limitation. Did the study offer any solutions?
Actually, yes. They found a surprisingly simple but effective trick.
What is it?
Just duplicating the ultra-short query. So if your query is sort list, you just feed the model sort list.
Seriously, just repeat it.
Yep, doubles the token length without changing the meaning. And apparently this significantly improved the cosine similarity scores and the actual search results for those short queries.
Huh. That's a neat practical takeaway. So the improvement isn't some hidden bias. It's literally just giving the model more input signal to work with.
Exactly. It helps the model get a better grasp on both the code's context and the query's intent when the query itself is very brief.
Okay, fascinating stuff. So let's try to wrap up this deep dive. What are the main takeaways?
Well, the big story is the transformation. Decoder-only LLMs might start surprisingly weak at code search, right out of the box, in that zero-shot setting.
Right, significantly weaker than older encoder models initially.
But with the right kind of fine-tuning, specifically supervised contrastive learning, maybe after some pre-training adjustments, they become incredibly effective.
So effective, they often outperform those traditional encoder models, especially on generalization.
Exactly. With CodeGemma really standing out of this study after fine-tuning.
But there's still that challenge with ultra-short queries. That needs more work.
Definitely. Optimizing for those very brief, low-context searches is still an open area.
So thinking bigger picture, what does this mean for developers, for software development?
Well, consider the implications. These fine-tuned decoder models are much better at handling longer, more natural language queries and understanding complex, lengthy code snippets.
Which sounds much closer to how a human might actually ask a question or describe a problem.
Precisely. So how might this impact your workflow if you're a developer? Or how you search for information in any complex domain?
It feels like we could move towards much more sophisticated, nuanced search tools. Less keyword guessing, more actual understanding.
I think so. This research suggests we're really just scratching the surface of leveraging these powerful models. It could make finding that needle in a haystack piece of code or information much, much easier in the future. Maybe those frustrating search sessions become a thing of the past.
A future without endless scrolling through irrelevant search results. Sounds pretty good.
Definitely something to look forward to.